The cosmos has long captivated humanity, but it's the alluring possibility of extraterrestrial life that truly fuels our imagination. At the very edge of our solar neighborhood lies a fascinating planet, Proxima Centauri B, just 4.2 light-years away. Orbiting the star closest to our Sun, this distant world is particularly intriguing because it resides in the habitable zone, a region where liquid water might exist. Since water is a vital ingredient for life as we know it, Proxima Centauri B stands out as a prime target in the quest to find life beyond Earth. But how could we ever hope to reach it? For centuries, the idea of interstellar travel remained a dream, a distant fantasy reserved for science fiction. Today, however, technological advancements are finally making this dream a reality. Enter the swarm of Pico spacecraft, small autonomous probes that could one day journey across the stars. But the road to Proxima Centauri B is filled with obstacles that demand innovative solutions. Can humanity push the boundaries of space exploration and answer the age-old question, are we alone in the universe? As we set out on our journey to explore Proxima Centauri B, we must first ask, why is this exoplanet regarded as one of the most promising candidates for life? What distinguishes it from the myriad of planets we've discovered? The answer lies in its unique location. Proxima Centauri B orbits within the habitable zone of its star, a region where conditions are just right for liquid water to exist on its surface. This is a vital factor, as liquid water is essential for life as we know it. Scientists believe this rocky exoplanet might share some similarities with Earth. Could Proxima Centauri B be our best chance at uncovering alien life? Such a discovery would profoundly reshape our understanding of our place in the universe. The technological challenge of interstellar travel looms large. If Proxima Centauri B holds the potential for life, the next question we face is, how do we reach it? The distances involved in interstellar travel are staggering. Even if we could travel at the speed of light, it would still take over 4 years to reach Proxima Centauri. But traveling at that speed is beyond our current capabilities. So how do we overcome these challenges? Pico's interstellar travel presents significant challenges, but the solution may lie in laser-powered light sails. These advanced technologies have the potential to propel small probes to relativistic speeds, allowing them to reach another star in as little as 20 years. By using powerful ground-based lasers, miniature spacecraft could achieve speeds up to 20% of the speed of light. This breakthrough would dramatically shorten the time needed for interstellar journeys, bringing distant exoplanets like Proxima Centauri B within reach for human exploration. How do we overcome the challenges of traveling such vast distances in space? A laser beam fired from Earth would push a light sail, a thin, reflective surface attached to a probe, accelerating it to extraordinary speeds. This technology could make it possible to send a small probe to Proxima Centauri B within 20 years, a time frame far shorter than what current technologies would allow. Laser propulsion will get us to Proxima Centauri B faster than ever before. But once we arrive, we face another challenge: how to gather and transmit meaningful data over vast distances. This is where the concept of Pico spacecraft swarms comes into play, providing the means to gather data from multiple points on the planet while overcoming the inherent time lag and weak transmission signals. How can we gather valuable data from Proxima Centauri B, a planet located so far away, when conventional communication methods are too slow and ineffective? This is where the idea of Pico spacecraft swarms becomes essential. A single spacecraft journeying to Proxima Centauri B would encounter significant difficulties. How could it collect and transmit enough information to make such a monumental mission worthwhile? Rather than depending on just one probe, scientists are exploring swarming technology, deploying a fleet of small, autonomous spacecraft that can collaborate as a unified team. A swarm of Pico spacecraft will be launched, each probe operating autonomously but working in unison, making the swarm highly redundant. If one probe fails, the others can continue the mission without interruption. The probes will coordinate their movements and communicate with each other, ensuring the entire swarm can cover Proxima Centauri B from multiple vantage points, sending back a powerful combined signal to Earth. Why is a swarm of Pico spacecraft the optimal method for exploring distant planets like Proxima Centauri B? The key is redundancy and extensive coverage. With more probes, the swarm can gather data from a broader range of locations on the target planet, enhancing the likelihood of discovering something important. More probes mean better coverage and a stronger collective signal sent back to Earth. By synchronizing the probes and combining their data, the swarm can amplify the signal, overcoming the challenges of distance and weak transmission. By synchronizing the probes in a swarm, we can amplify the signal, boosting the chances of transmitting and receiving valuable data on Earth, enabling humanity to explore the unknown with fewer resources. Exploring the unknown resources. But there's a paradox in all of this. These probes are tiny, no bigger than a grain of rice, and they have limited resources. How can such small spacecraft with minimal onboard power contribute meaningful scientific data? The answer lies in the efficiency of modern technology. These Pico spacecraft will be equipped with micro-miniaturized atomic clocks to maintain synchronization across the entire swarm. They'll also carry miniaturized sensors that can measure a variety of scientific parameters, including the planet's atmosphere, temperature, and radiation levels. The probes will be powered by solar panels that produce just enough energy to sustain their operations throughout the long journey. But how can small spacecraft with limited power and resources gather enough data to be valuable? At the heart of this technology are dedicated scientists and engineers who view this mission not merely as a project but as a pursuit of humanity's most ambitious dream: to uncover life beyond Earth. For Dr. Emma Young, an engineer on the team, this mission symbolizes a lifetime of commitment. Exploring the stars isn't just about technology, she says. It's about finding the answers to the questions that keep us up at night. Are we truly alone in the universe, or is there life just waiting to be discovered? This personal dedication is what fuels the work on this mission. Their atomic clocks allow them to maintain precise synchronization, ensuring that they work in unison to gather and transmit data. By sharing data across the swarm and transmitting combined signals, the probes can overcome the weak transmissions of individual probes. This collaborative effort means that the swarm can gather far more information than a single spacecraft could ever hope to collect. Autonomy. Another challenge for the swarm is the absence of real-time communication with Earth. Due to the immense distance between Proxima Centauri and Earth, any signal sent back would take years to arrive. As a result, the swarm of Pico spacecraft must function autonomously, making decisions independently without relying on instructions from Earth. What happens if the probes lose contact with Earth? The great distance to Proxima Centauri means the mission will face a significant time delay. Any data sent from the probes will take over 8 years to reach us. This makes real-time decision-making impossible. Instead, the swarm of Pico spacecraft must rely on autonomous decision-making using pre-programmed algorithms to prioritize data collection and transmission. This means the mission will need to operate independently with minimal human intervention, relying on the advanced AI systems on board the probes to adjust to new conditions and make real-time decisions based on the data they collect. Instead, the probes will be pre-programmed to operate autonomously, with each probe making decisions based on its environment and the data it collects. The probes will focus on transmitting the most crucial data, ensuring vital information is sent back to Earth. In the event of a probe failure, the others will keep gathering and transmitting data, allowing the mission to proceed despite any challenges. The swarm's ability to operate autonomously is a key element of the mission, ensuring the spacecraft remains functional despite the vast distances and the time delay between Earth and Proxima Centauri B. The probes will be equipped with advanced AI systems that allow them to adjust their operations based on the data they gather, ensuring that the mission continues even in the absence of real-time communication. As we explore the potential of reaching Proxima Centauri B, we see that the journey is not only a scientific quest, but a technological challenge of immense proportions. From the laser-powered light sails that will propel us to distant stars, to the swarm of Pico spacecraft that will collect valuable data from Proxima Centauri B, this mission pushes the boundaries of what we thought was possible. The challenges are far from behind us. How will we address the time delay, communication obstacles, and the potential for failure? Will we find signs of life on Proxima Centauri B, or will we realize that the universe remains as empty as it always has been? Scientific discovery. As we prepare to send Pico spacecraft swarms to Proxima Centauri B, the potential for groundbreaking discoveries becomes more tangible. The key question on scientists' minds is, what can we learn from exploring Proxima Centauri B and its atmosphere? The probes will focus on identifying biosignatures, chemical indicators that may suggest life. One of their primary tasks will be analyzing the planet's atmosphere for key signs such as oxygen, methane, and other organic compounds, which are often linked to biological processes on Earth. If found, these could point to life on Proxima Centauri B. Additionally, scientists aim to gather insights into the planet's climate, geology, and surface conditions, exploring whether it has undergone processes similar to Earth's that could support life. This data could reveal whether Proxima Centauri B has supported life, either now or in the past, and offer valuable information about how life might emerge on planets around red dwarf stars. But the discoveries extend beyond life. By studying the planet's geology, scientists could uncover clues about its formation, helping us understand how planets evolve in various stellar environments. This mission could provide insight into not only Proxima Centauri B's potential for life, but also the broader processes shaping planetary systems across the galaxy. Ethical dilemmas. As we explore distant planets, we must confront the ethical challenges that arise. What are the ethical implications of sending probes to potentially habitable planets like Proxima Centauri B? Concerns go beyond contamination. Introducing Earth-based microorganisms could alter any existing alien life forms. Ownership of discoveries is another issue. Should these findings belong to the nation or organization that funded the mission, or should they be shared globally? There's also the moral dilemma of whether we should study potentially habitable planets at all, especially if they may harbor life. While spacecraft are sterilized before launch, contamination remains a significant ethical concern. As space exploration transitions from government-led efforts to a more collaborative global endeavor, questions about ownership and responsibility become even more important. Finally, if Proxima Centauri B hosts life, even at its most primitive stage, should we study it or leave it untouched? There is no clear answer, but as interstellar travel progresses, this issue will require serious reflection and possibly international agreements to ensure responsible exploration.